Hello, and welcome to our segment on special relativity. You'll recall that in our last segment on the speed of light, Michelson and Morley demonstrated that the speed of light was the same for all inertial observers. The first impact of this discovery was that the Galilean transformations that we've been using for centuries was incorrect. New transformations were needed, and these new transformations had to satisfy two key requirements. One, no matter how we add speeds, the speed of light had to come out the same, and at low speeds compared to the speed of light, we had to get the Galilean transformations. In the years following Michelson-Morley's experiment, a number of physicists and mathematicians went to work on this problem. People like George Fitzgerald, Henry Poincaré, and Hendrik Lorentz. They came up with these transformations, now called the Lorentz Transformations. In this segment, we'll see how these transformations required that time was stretched, dilated, and distance was contracted in order to satisfy the two main requirements. And we'll also see how Einstein put it all together with just two postulates. One of the most unusual consequences of the speed of light being a constant for all observers is that the flow of time itself is not immutable. It too must be relative to the inertial frame's motion. Here's a good way to see why this must now be the case. Here's a simple light clock. Light travels between mirrors at the end of a known length. For our purposes, we'll make it a very long length, say 150,000 kilometers. That way, one round trip will mark 1 full second. Now, if we put the clock into motion with respect to a ground-based observer, we see that the light has to travel further. And because its speed is constant, it will take longer. The moving light clock is therefore running slower than a stationary duplicate. This is called time dilation. It's the geometry of the situation that gives us the conversion factor. If I were on a 10-hour flight from LA to Paris, traveling at 800 kilometers per hour, I would lose just under a nanosecond. Way too small to notice. But for faster moving spacecraft, it can be quite significant and critically important. For example, orbiting GPS satellites travel at 3,874 meters per second with respect to the Earth. They use cesium atomic clocks to keep time. They measure time to within 1 second in 1,400,000 years. But these onboard clocks lose 7,214 nanoseconds a day due to time dilation. If onboard clocks aren't corrected regularly based on Lorentz time dilation formula, the position data they produce would be off by kilometers in less than a day. Another consequence of the speed of light being a constant for all observers is that the size of an object shrinks along the line of motion when viewed by an observer in a different inertial frame. To see how this must also be true, we put a second identical clock on the moving frame, but this time we align it with the direction of motion instead of perpendicular to it. They tick at the same rate because they are identical clocks at rest together. They will also tick at the same rate for an observer on the ground, only they will tick slower, as we have already established. But the motion of the horizontal clock's mirror makes the distance the light has to travel different from the distance the light travels in the perpendicular clock. Here we see the perpendicular clock ticking 1 before the light in the other clock has even reached the other end, let alone returned. The only way to bring the clocks back into sync is for the length of the distance traveled horizontally to shrink. And given the Lorentz transformation for distance, this is exactly what happens. This is called space contraction. Here's a look at the new Orion spacecraft, fully decked out for the planned long journeys to the Moon, asteroids, and Mars. If we were traveling at the same speed as GPS satellites, it would look like this. If it were traveling at 0.9 times the speed of light, it would look like this. And if it were traveling at 0.99 times the speed of light, it would look like this. Unfortunately, we don't have the technology to take a measuring rod and accelerate it to almost the speed of light in order to measure how much it shrinks. But we do have the interesting example of muons created by cosmic rays in the upper atmosphere 15 kilometers above the ground. You'll recall from our segment on elementary particles in the How Small Is It video book that we discovered muons with cloud chambers on mountaintops and in high-flying balloons. We found that their half-life is only 2.2 microseconds. Traveling at near the speed of light, half the muons would decay with each 660 meters traveled. That would leave few, if any, reaching the Earth's surface, 15 kilometers away. Yet we measure about 1 per square centimeter per minute. That's around 90% of the estimated muons produced in the upper atmosphere, which is way too high a percentage, given the short half-life. This high count rate is explained using relativistic time dilation. The measured velocity of the created muons is 0.999986 times the speed of light. So, by time dilation, the half-life would be 189 times longer. This gives the muons time to travel up to 125 kilometers before half of them have decayed. And that's plenty of time for most of them to reach the surface in line with the numbers observed. But what does this look like in the muon's own reference frame, where it is standing still and the Earth is approaching at 0.999986 times the speed of light? It will only last 2.2 microseconds. How will it make it to the surface? This is where space contraction comes in. The 15 kilometers of atmosphere is shrunk. For the muon, the distance to the surface is only 79.4 meters. Most of them will reach it in 2.2 microseconds. Now that we have a feel for the effects of special relativity, let's look at how fast things can go in this relativistic world. You'll recall from our previous segment on the speed of light that the classical transformations simply added the speed of movement in a reference frame to the speed of the reference frame itself. Here we see the person walking on the moving train. We simply added his walking speed to the train's speed to get the speed seen by an observer on the ground. In special relativity, the clock on the train is running a bit slower, and the distance the person walked is a little bit shorter, as seen by the observer on the ground. So this calculation of the total velocity is a bit less than the Galilean calculation. But at these speeds, it is too small a difference to notice. Now let's shift the supertrain into high gear and say its velocity is 8/10 of the speed of light. And the person on the train kicks the ball at 1/2 the speed of light. If the Galilean transformations were correct, the person on the ground would add these together and see the ball traveling faster than the speed of light. But to keep the speed of light a constant, the new relativistic equations tell us the person on the ground would see the ball traveling a lot slower than that, at 9/10 the speed of light. You can even see that, with the relativistic equations, if the train was traveling at 0.8 times the speed of light, and a light was turned on, the person on the ground will see the light traveling at the speed of light, just like the person on the train will. In the most extreme case, suppose we had two photons traveling towards each other. Here's the northern hemisphere's summer triangle, with Vega, Altair, and Deneb. Let's say one photon is traveling from Deneb to Altair, and the other one is traveling from Altair to Deneb. Of course, each of them is traveling at the speed of light, so we would see their closing speed at 2 times the speed of light. But if we look at it from the point of view of one of the photons, we see that it sees them closing at the speed of light, not twice the speed of light. You'll recall from our segment on the microscopic in the How Small Is It video book that momentum is mass times velocity. Another interesting consequence of the speed of light being a constant for all observers is that the momentum of an object increases without bound as its velocity approaches the speed of light. This increases the amount of energy it takes to increase its speed even more. Our best example of this is the Large Hadron Collider at CERN, where the Higgs boson was found. To begin with, protons are accelerated down a linear accelerator. By the time they reach the first cyclotron, they're traveling at 1/3 the speed of light. We can use this as the starting momentum. If we had used Galilean transformations, we would be off by 5%, and the linear accelerator would not work. The first booster accelerates the protons to 91.6% of the speed of light. This speed more than doubles the momentum. The protons are then flung into the proton synchrotron. They circulate here for 1.2 seconds, reaching 99.9% of the speed of light. At this speed, their momentum has increased by more than 60 times. The protons are then channeled into the superproton synchrotron. This is a huge ring, almost 7 kilometers in circumference. The best that it can do is to increase the velocity of the protons by around 8%, to 99.9998% of the speed of light. The proton's momentum has now jumped by over 1,400 times its momentum at the end of the first acceleration. Finally, the Large Hadron Collider accelerates these incoming protons to 99.9999964% of the speed of light. The proton's momentum tops out at 10,562 times its original momentum. At this level, Galilean transformations would be off by over 99.9%. The fact is that as the velocity gets closer to the speed of light, the momentum increases without bound, and the energy required to get it even closer to the speed of light grows to be more energy than exists in the universe. This is one of the reasons why we say that nothing with mass can ever reach the speed of light. The operations of the Large Hadron Collider at CERN confirm this relativistic momentum increase, just as the operations of GPS satellites confirmed relativistic time dilation, and cosmic ray-created muons confirmed relativistic length contraction. The last non-intuitive consequence of the speed of light being the same for all observers that we'll cover is that the idea that things can happen at the same time no longer has meaning across inertial frames of reference. In other words, there is no such thing as at the same time for different inertial frames. To see this, we'll go back to our train example. Here, the observer on the train is in the middle of the car, and as he moves past the observer on the ground, lightning strikes the front and back of the train car. The light from both strikes travel the same distance at the same speed and reach the observer on the ground at the same time. He correctly concludes that lightning hit the front and back of the train car at the same time. The person on the ground also notes that the light from both strikes travels to the person on the train at the same speed, but because the person on the train is moving in the direction of the front lightning strike, it doesn't have as far to go, and therefore it reaches him first. But how does this all look to the person on the train? In his reference frame, he is not moving forward. The person on the ground is moving backward. He knows that he is also the same distance from the lightning strikes, and he also knows that the speed of light is the same for both strikes. So for the front strike to reach him first, it must have happened first. If they had happened at the same time, they would have reached him at the same time. The person on the train sees the light from the first strike start traveling to the person on the ground before the light from the second strike. But because he is moving in the direction of the second strike, they get to him at the same time. Who is right? They are both right in their own reference frame. They are simply measuring what they see. What is simultaneous at two locations in one reference frame may not be simultaneous in another reference frame. What happens in two places at the same time on Earth will not be happening at the same time if we're viewing them from Venus. Simultaneity is relative, along with time, distance, speed, and momentum. All these effects were known before Albert Einstein's theory of relativity was published, and he was familiar with them. The thinking by 1905 was that there is still an ether that represented nature's absolute reference frame, but that time dilation and space contraction made it impossible to detect. The ether was held to exist for two main reasons. One, it gave light a medium to propagate through, and two, it provided for an absolute frame of reference like the one we used to have with the Earth. With it, we could claim that there is such a thing as simultaneous events in two places, in at least one preferred by nature reference frame. Einstein parted with this theory for two reasons. One was that he studied James Maxwell's equations that showed the speed of light was the result of empty space's resistance to the formation of an electric field, permittivity, and a magnetic field, permeability, as we covered in the microscopic segment of our How Small Is It video book. So there was no need for a propagating medium like the ether. Empty space will do just fine. And relative motion would not change these basic properties of empty space, thus making the speed of light the same for all observers. The other reason was more philosophical. What does it mean to postulate the existence of a thing and then explain that it cannot be detected? In the end, he accepted the idea that there is no universal frame of reference, and all time, space, and simultaneity were relative for all inertial frames. In Einstein's paper, he articulated two postulates. One, the laws of physics are the same in all inertial reference frames. This means that formulas like force equals mass times acceleration will hold in all inertial reference frames, and all experiments run the same in all inertial reference frames. For example, if you drop a ball standing at home, it falls straight down to your feet. The same thing happens if you are standing on a moving train. The ball falls straight down to your feet. Postulate number 2 is that the speed of light in a vacuum has the same value in all inertial reference frames. With these two postulates, Einstein generated all the relativity equations of Lorentz and others. It was his study of relativistic mass, momentum, and energy that led Einstein to the famous equation E equals mc squared. No one else had made this relationship between mass and energy. Today's nuclear power industry is a testament to the accuracy of this special relativity formula. We can now graph light using our space-time coordinates. For this, we use the distance light travels in 1 second for the units on the x-axis. This gives us the line running diagonally up the right side for light moving in the positive direction. At this scale, we cannot distinguish between the speeds achieved by snails, animals, cars, planes, and rockets from the line that represents standing still. Here's the line for protons at the end of the Large Hadron Collider's linear accelerator, traveling at 1/3 the speed of light. And, at this scale, the line for protons in the LHC itself is indistinguishable from the speed of light. Now we can run the light line up the left side for light moving in the negative direction. If we then extend the x-axis line to be a plane that we'll use to represent three-dimensional space, we can rotate the light line 360 degrees to create a cone, the light cone. This is the four-dimensional space-time graph. A point on this graph represents an event with 4 coordinates: x, y, and z for space, and t for time. A mathematician named Hermann Minkowski developed the geometry for Einstein's space-time, so you may sometimes hear space-time referred to as Minkowski space. The four-dimensional length of a line in Minkowski space is referred to as proper time or proper distance. Space-time inside the cone is called time-like because the length of connected points have positive proper time. This makes all points inside the light cone reachable. In other words, it is possible for an event at an earlier time within the cone to be the cause of an event at a later time within the cone. At the speed of light, the lines connecting the events run up the edge of the cone, and the four-dimensional length of the line connecting these events, proper time, is 0. Cause and effect can still hold. The space outside the cone is called space-like. The proper time of the line connecting a point inside the cone with a point outside the cone will have a negative length. And like the boat example in our speed of light segment, where negative time simply meant that you could not get there from here, so the negative proper time simply means that you cannot get from one of these points inside the cone to the other point outside the cone. In other words, no event from within the cone can ever be the cause of an event outside the cone. If we go back in time, as well as forward in time, we get the full space-time diagram. Here we see that no past event outside the cone can be the cause of any event we see today. We'll end this segment with a look at the famous twin paradox. It goes like this. Suppose two 20-year-old twins start out together on the Earth. One of them gets into a spaceship for a trip to Vega, traveling at 99% of the speed of light. The person on the Earth sees the trip taking just over 25 years, and the trip back taking the same amount of time. She is over 70 years old when the ship carrying her twin sister arrives back on Earth. But she also observes that her twin's clock ran a good deal slower than hers during the trip. Her twin is aging more slowly than she is. At 99% of the speed of light, time dilation would have the twin at just over 27 years old on her return. But from the point of view of the twin on the spaceship, she is motionless, and the twin on the Earth is moving away and back. And like our cosmic ray muons, she sees the distance to Vega at only 3.5 light years due to space contraction. She also sees the twin on the ground aging slower than her over the 7-year journey. By her observations, her sister will be only 1 year older on her return due to time dilation. That's 6 years younger than she is, not 27 years older. How can it be that they are both older than the other? This is the paradox. The first thing to notice is that the twin in the spaceship spends several periods of time being accelerated, meaning it is not an inertial frame. This paradox is fully resolved by Einstein's general theory of relativity. We'll cover that in our next segment.